Today we bring you the second video in the mass ranges of stars low, intermediate, and high video series. If you have not watched the first video in the mass ranges of stars low, intermediate, and high video series, please watch that video before watching this video. That video is in the playlist 8 Stellar Properties: Mass, Luminosity, Temperature, and Chemical Composition. We invite you to stay until the last minute of this video. High mass stars, defined as those with initial masses exceeding approximately 8 to 10 solar masses, represent the most spectacular and influential objects in stellar astronomy. Despite comprising less than 1% of all stars, these cosmic behemoths dominate the observable properties of galaxies through their enormous luminosities and dramatic evolutionary processes. High-mass stars shine millions of times brighter than the sun and profoundly impact their local environments through intense stellar winds and eventual explosive deaths. The upper mass limit for stars remains somewhat uncertain, though current observations suggest that stars can potentially reach 150 solar masses or more under favorable conditions. The most massive stars observed include objects like R136A1, which may exceed 250 solar masses, though such extreme masses require special formation conditions and likely involve continued accretion after initial stellar birth. These ultramassive stars exist at the edge of stability, where radiation pressure from an intense nuclear burning approaches the gravitational forces holding them together. High-mass stars burn through the complete sequence of nuclear fusion reactions, progressing from hydrogen burning to helium, carbon, neon, oxygen, and finally silicon burning. Each successive burning stage requires higher core temperatures and densities, occurring over progressively shorter timescales. Silicon burning produces iron peak elements, including iron, nickel, and cobalt, which represent the endpoint of energy-producing nuclear fusion. Beyond iron, further fusion reactions require energy input rather than releasing energy, marking the end of stable nuclear burning. The main sequence lifetimes of high-mass stars are remarkably brief compared to their lower-mass counterparts. A 40 solar mass star may spend only about 1 million years burning hydrogen in its core, while a 15 solar mass star has a main sequence lifetime of roughly 10 million years. These short lifetimes reflect the enormous energy output required to support such massive stellar structures against gravitational collapse. The luminosity of high-mass stars scales approximately as a fourth power of their mass, meaning that doubling the stellar mass increases the energy output by a factor of 16. High-mass stars evolve through several distinct phases during their post-main sequence evolution. After exhausting core hydrogen, they expand to become red supergiants, with some reaching sizes that would engulf the orbit of Jupiter if placed at the Sun's position. Many high-mass stars also pass through blue supergiant phases, particularly those with initial masses between 20 and 50 solar masses. These blue supergiants have surface temperatures between 10,000 and 50,000 Kelvin and luminosities ranging from 10,000 to over 1 million times that of the Sun. The most massive stars may experience luminous blue variable phases, characterized by dramatic instabilities and episodic mass loss events. These stars, exemplified by objects like Eta Carinae, can brighten by factors of 10 or more during outburst events, ejecting substantial amounts of material into their surroundings. The instability likely results from radiation pressure approaching the Eddington limit, where the outward pressure from the star's luminosity nearly balances gravitational attraction. Some high-mass stars evolve into Wolf-Rayet stars, extremely hot objects with surface temperatures exceeding 30,000 Kelvin that exhibit strong, broad emission lines in their spectra. These stars have lost most of their outer hydrogen layers through intense stellar winds, exposing the products of nuclear burning in their cores. Wolf-Rayet stars represent an advanced evolutionary phase for stars with initial masses above approximately 25 to 30 solar masses. The ultimate fate of stars depends critically on their initial mass, with each mass category following distinct evolutionary endpoints that reflect the different physical processes governing their internal structure and evolution. These final stages represent some of the most energetic and consequential events in the universe, responsible for dispersing heavy elements throughout space and triggering new generations of star formation. Low-mass stars end their lives relatively quietly compared to their more massive cousins. When these stars exhaust their nuclear fuel, they expel their outer layers through gentle stellar winds, creating beautiful planetary nebulae that glow with the light of the hot white dwarf remnant at their centers. The white dwarf represents the final stellar core, compressed to approximately the size of Earth but containing as much mass as the Sun. These incredibly dense objects are supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy states. White dwarf stars gradually cool over billions of years, eventually fading to become cold, dark objects called black dwarfs, though the universe is not yet old enough for any white dwarfs to have completed this cooling process. The maximum mass for a stable white dwarf is approximately 1.4 solar masses, known as the Chandrasekhar limit. White dwarfs that exceed this mass threshold cannot be supported by electron degeneracy pressure and will undergo catastrophic collapse. Intermediate mass stars generally follow similar evolutionary pathways to low mass stars, ultimately producing white dwarf remnants after ejecting their outer layers through planetary nebula formation. However, the white dwarf produced by intermediate mass stars tend to be more massive and hotter than those from lower mass progenitors. Some intermediate mass stars, particularly those near the upper end of this range, may produce white dwarfs that approach or exceed the Chandrasekhar limit, potentially leading to Type Ia supernova explosions if additional mass is subsequently accreted from a companion star. High-mass stars experience the most dramatic and violent deaths in the universe through core collapse supernova explosions. When these stars exhaust their nuclear fuel, their iron cores grow until they exceed the Chandrasekhar limit, at which point electron degeneracy pressure can no longer support the stellar core against gravitational collapse. The core collapses in less than a second, rebounding when it reaches nuclear density and launching a powerful shock wave that tears through the stellar envelope. Core collapse supernovae release approximately 100 times more energy than the Sun will produce during its entire 10 billion-year lifetime, all within the span of seconds to minutes. These explosions are visible across billions of light-years and temporarily outshine entire galaxies. The expanding supernova shock wave enriches the surrounding interstellar medium with heavy elements forged in the stellar core and during the explosion itself, providing the raw materials for future generations of stars and planets. The remnant left behind by a core collapse supernova depends on the mass of the collapsing core. Cores with masses between approximately 1.4 and 2 to 3 solar masses form neutron stars, incredibly dense objects composed primarily of neutrons and supported by neutron degeneracy pressure. A typical neutron star contains as much mass as the Sun compressed into a sphere only about 20 kilometers in diameter, resulting in densities comparable to atomic nuclei. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. Stellar cores that exceed roughly 2 to 3 solar masses at the time of collapse will not be stopped by neutron degeneracy pressure and continue collapsing to form stellar mass black holes. These objects represent the ultimate triumph of gravity over all other forces, creating regions of space-time where the gravitational field is so strong that nothing, not even light, can escape once it crosses the event horizon. Stellar mass black holes typically range from about 5 to several tens of solar masses, though the relationship between initial stellar mass and final black hole mass remains complex due to mass loss during stellar evolution. Recent observations have identified possible gaps in the mass distribution of compact objects, particularly a lower mass gap between the heaviest neutron stars and lightest black holes. This gap, spanning roughly 2 to 5 solar masses, may reflect the physics of the core collapse process or could be filled by objects formed through different mechanisms, such as neutron star mergers. An upper mass gap has also been proposed for stellar mass black holes, suggesting that direct stellar collapse may not produce black holes with masses between approximately 50 and 150 solar masses. This video is getting long, so I'll stop here. Expect the rest of this in the next video. You can see more valuable videos by clicking on the card shown here. If you want to see our next video as soon as it comes out, subscribe to our YouTube channel and click the bell icon. Thank you very much for watching the video so far.